All right, we're going to today talk about human error. This is kind of a standalone topic, one lecture on this. And this is an introduction to um, a topic that's really broader than one lecture. It's really something that it permeates a lot of the cognitive side of ergonomics. We spent a lot of time on the physical side of ergonomics. We spent some time on the work design, work measurement type uh, of, of science. Now we're going to shift gears a little bit to the cognitive side. Now, on your syllabus, this is a part of the cognitive assessment block. All right, and the next lecture will be on cognitive assessment as well as the lab that we're going to do. But um, this particular one is kind of background information so that when we do the cognitive assessment, we sort of have this idea of what it is to think about the decisions and the mistakes and the problems that arise when humans and other systems really interact. That's really what human error is talking about. You might be familiar with um, accident investigations where human error are quite often contributors. Okay, human errors, human mistakes. And this is relevant, but it's not the only thing we really focus on. So that's kind of where we are with this. Um, I'm going to uh, probably try to go through this fairly quickly. At least it's my hope that we'll be under an hour, so we can do it all in one sitting. Some of you are way too young for this, but there may be some in the class that remember this or at least heard about it. Okay, um, back in 2000, during the presidential election, it was a hotly contested election, and if you know your history or you remember, this election was so tight that it took weeks of legal wrangling before it could officially be certified to know that George Bush had actually won the election over Al Gore. Um, One of the primary reasons for the dispute was the state of Florida and how various counties within the state handled their ballot counting processes, as well as actually the design of some of the ballots. And every county had the ability to kind of do their own ballot style if they wanted to. And I believe, if I remember right, the state of Florida requires um, each candidate to not just be on the ballot from the state level, but maybe it's in the congressional district level or even in the county level. So every ballot could be different. This was the Palm Beach County, which is a large county there in southern Florida, and this was their ballot. And as you can see, um, the there are these holes down the middle here, and then there are the candidate names, and you can see both president and vice president are listed there. There are those names and arrows that point you to the hole that they're supposed to be related to, right? You're supposed to know if you want to vote for candidate number 3 or whatever, you go to the hole that the arrow points to. Unfortunately, this is not as obvious as it sounds like, because perhaps if I want to vote for George W. Bush, I realize that you can sort of see there's two columns of names, and the Republican candidate is kind of a little above the Reform Party candidate on the right, so it must be first, right? So it's the first one. But you can see that the Reform Party candidate is kind of a little higher than the Democratic candidate, right? So the Reform Party candidate might look to be the second one, and that's true, right? It's candidate number 4, there's the arrow, it points there. And that's correct. So the second punch here would be for Reform Party candidate. Well, that's all well and good if you make a recognition of that that's how this ballot is sorted. However, people who are used to reading columns and then going to the next column and looking for additional uh, perhaps ballot punches, maybe here on the right side, far right um, of this ballot, might think that the second hole punch um, is a vote for Democratic candidate Al Gore. So if you wanted to vote for Al Gore, you vote according to that way of thinking. You would vote in the second hole because he's the second candidate listed in this first column, and also because the Republican and Democratic candidates are certainly the more popular candidates. I mean, 95% or so of the votes were probably going to be one of those two candidates. So um, So it makes some sense to some voters that, of course, they would be the top candidates. Um, but that's not the case. Okay, so that means if I'm planning to vote for Al Gore and I make that mistake, I click the second hole. Well, the second hole gives me a vote for Pat Buchanan. So that's a potential for human error. And you may say, well, we can figure it out. That's true if you know that there's a reason to do very close investigation to figure it out. But if you don't know, if you've been doing this for a long time, or if this ballot is confusing, or perhaps if you're elderly and your vision is a little bit challenged, these little arrows with this very small leaders and large arrowheads are not very good examples. They don't, large arrowheads with very little tail do not really point very well. That's another problem. As well as the numbering system. Why does it start at 3? Where's 1 and 2? Right? So it's a little confusing. And it goes 3, 4, 5, 6, 7, 8, 9, 10 back and forth. And then 11 and 12 are in a row, or there is no 12 perhaps. That's 13. This is very confusing. Okay? And there were lots of complaints. And indeed, in this county, there were a lot more Reform Party votes than the demographic and the exit polling would have led to believe. Whether or not that means that the election actually was affected directly by this, or if this is just kind of an example of something that could have gone wrong, I'll leave that for you to decide. Perhaps you've seen this sign. I would ask you to tell me what it means. And I'll give you some options, okay? Does it mean that you should walk on the left, ride your bike on the right? Okay. Does it mean that there is no riding of the bike at all? This is not in this direction. You cannot ride your bike this way. Or does it mean something else? And some of you have seen this sign. This sign is actually just outside of the Industrial Engineering Building there on Kansas City, on the sidewalk there next to Kansas City Street. So what does it mean? Well, it's actually supposed to mean that the sidewalk is divided into 2 parts, 2 lanes, if you will. And the lane closer to the building here, which is the left lane from this vantage point, is for pedestrians only. And then the lane closest to the street, which would be the right lane in this side, is for bicycles only, right? Which perhaps is what you get from this part of the sign. Now there's these tree planter boxes and some trash cans and things that actually separate those lanes so they don't really overlap. And then there's even some signage on the actual concrete itself, some paint that kind of tells you. But the confusing part is the pedestrian lane is 2-way. I can go, I can go east or I can go west and still be in this lane, and you just obviously dodge the people as you go. But the bike lane is intended to be a 1-way lane. And because the traffic direction closest to this direction, this would be traffic that's coming towards me as the viewer here looking at this sign on the street, they've designed the bicycle traffic to also be coming towards me, coming towards you in this picture. So we'd be looking towards the oncoming bicycle traffic if you were appropriate. So that's what the wrong way sign is saying. It's saying on the right here, expect there to be bicycles, but they're only coming towards you. You shouldn't be biking, what amounts to be towards the east here. You should be, that's for the other side of the street, right? But that's not very clear. In fact, you may not even know what I'm still talking about. It's really not very clear. And the fact that they have 2 different signs and bicycles keep right but don't go this way is pretty confusing. You've probably seen one of these before. We have one on our campus. This is from a different campus. Here you have a large sidewalked area, patio of some kind with a nice small wall border, and you kind of have a dead end here. And obviously people want to get to this area over here, this building. And rather than leaving the dead end and going a long way, they just cut through this, what probably intended to be a nicely manicured flower garden or plant garden of some kind, ivy, whatever that is. But now that's all dead because everyone and their brother goes this way because it's more direct. People want to be here. This sidewalk kind of leads you to believe that you could walk here, right? Why else would there be sidewalk? But then you have to turn around. Okay, obviously the people don't do what the designers thought they would do. They instead just cut through the plants. Here's another example, different campus. This one's a little worse in my opinion because you actually have a crosswalk that ends here. There's a wheelchair ramp even, and you get here and you want to be here, but you cannot get there. So the crosswalk, you don't cross at another location. And my old campus had one of these too. There was a crosswalk, it led here, and then there was no sidewalk, and then there was a sidewalk like 50 feet to the right, but you couldn't cross there, so you kind of had to cross, skip over, cross, and of course no one did that. They just cut through the grass, so there was lots of dead grass. So it was a dumb design. This is the same thing. People obviously want to go, kind of in this diagonal direction. Maybe there's another building over here they want to get to or something like that. So why isn't there a sidewalk there, especially if the crosswalk demands that they actually go this way? And you can see that the solution here is, rather than connecting these two with a nice sidewalk, was to put up these two signs on either side that say, down here you can see, please use sidewalks. In other words, we've recognized there's a problem. Our solution is to tell you not to do it anymore. Let's see how that works, right? This is one that you've probably seen a million times in various gas stations, if you're a driver at least, and that is different cars choose different sides of the vehicle to place the fuel door or the gas tank, if you will. The gas tank's actually not on necessarily one side or the other, but the door or the hatch leading into the gas tank so you can refuel the car is on one side or the other. And so that is kind of annoying for some of us. Usually, if it's your main vehicle, you're going to get used to it, right? But then you switch vehicles and it's on the other side. It takes you a month or two to remember, and depending on how often you get gas, it could be longer than that. And then at other times, even out of the blue, a year or two later, you're like, why did I go to this side of the car for gas, right? So that's one issue. Another issue would be like if you're borrowing a car, or if you have 2 or 3 vehicles in your household and they're different, and you drive one primarily, but then you switch, or you get a rental car or something like that. Now, why? It seems like a small thing. Well, you just back up and turn around. But if you've gone to many of the gas stations that I go to, there's often a pretty long line, a couple cars you got to wait through. So you wait through the line, and then, oh, goodness sakes, I'm on the wrong side. You have to go wait again. So it's a little longer than just a few, a 30-second mistake. Or what's even more challenging is some gas stations have one-way direction next to the gas pumps, which is to say that on one side of the pump, right, you can pull in, and if that fits your tank, then great. But if it's not, you cannot turn around. Well, I guess what I'm saying is, suppose that all the ones on your side of the tank are full. You cannot just go past and turn around and come the other direction on the other side, which would still be appropriate, because that's a one-way. That's designed for cars of the other side, but it's not an equal distribution in most cases. By far, more cars have the fuel door on the driver's side, on the left side of the vehicle. So a lot of times in these one-way directional gas stations, you'll have cars with the driver's side tank like lined up, and then the area on the other side of the pump that's for cars on the passenger side, there's just maybe 1 or 2 vehicles in the whole station using it, and there's all this empty things. So then what do people do? They violate the one-way direction, and so they pull in, they go the wrong way, but then you have some issues with traffic flow. There must be a reason for the one-way direction. So Sam's Club gas station is a good example here in town. If you want to go there and check it out and watch how many people violate what it says there to do. So anyway, this is an issue. This is one solution, right, to put a symbol here reminding you that the fuel door is on the left side of the driver's side of the vehicle. Again, if it's your primary vehicle, after some time, that's not going to be an issue for you. This is sort of more early on in your driving of a vehicle, or if it's a rental especially, that would be valuable, right? So there you go. This one is kind of interesting. I know at least one of you mentioned that you had a kitchen cutting board kind of like this, right? So you see up here in the A picture, you can see this drawer, this flat area, that's a pull-out cutting board. So you can see in B picture it pulls out, and you can use it as kind of extra kitchen counter space for your cutting, okay? Which is a little bit gross because I want to take that out and clean it a lot more than that, but anyway, so be it. But lo and behold, what happens is that the silverware drawer is directly beneath, right here. It's directly beneath the cutting board. And every time you have vegetables or something on the cutting board and you realize that you need something from the silverware drawer, what are you supposed to do? Okay, pull out the silverware drawer, you can't get to it. If you push the cutting board in, there go all your vegetables into the silverware drawer or something, or in the floor. So there's an issue. This one is, I found particularly interesting, is, and some of you know this, right? Refrigerator doors can be installed to be hinged on either side. A lot of refrigerators anyway, these classic kind of refrigerator designs anyway. And that's good because a lot of kitchens you don't know in advance. When you go and buy when they make refrigerators, they don't know in advance how many you're going to need to open on the left or on the right. And it just depends on your kitchen layout more than anything. And so they make it possible to do either. You don't have to go and buy a left refrigerator or a right refrigerator the way you would with some things, right? Like a softball glove, you have to buy the right hand. They make it so that you can do either one, right? The intent anyway. But in some cases, they have the handle cutouts already put on both sides, so you just have to hinge it whichever way you want. The problem is those handles still are visible there and can still be grabbed, and it's not the right side, right? The hinge is over here. So what happens if you pull right here? Well, nothing. It doesn't open. Okay, that can be very frustrating to people. Okay, and what happens when you try to open a door gently and it doesn't open? Almost everyone pulls much harder. And then what happens? Well, all your cereal boxes on the top of the fridge fall down, and all your magnets and everything fall down, and the fridge scoots out and it knocks something in the fridge over and it spills, and it still doesn't open because you're supposed to open it on the right side. Okay, that's an issue. So what could you do about that? Well, if you still need to have that capability, maybe you can have some blanks, right? So you pop out the recessed handles and you pop in some sort of smoothed off blanked areas that kind of cover over the handle area so it's easy to see that's not an actual handle. All right, so this one may be a little hard to see in the picture. So, well, it's not that bad, I guess. The thing I want you to notice is there is a green arrow to turn right, and there's red lights, a couple of them, telling you you can't go forward, you think. But in fact, this is a dead end, a T intersection, right? This is a parking lot over here. You're not really, it's gas station. I mean, you're not really going to be going over here all that much. Looks pretty dead, right? So actually, these red lights are for turning left, and then the green light is for turning right. So right now you can turn right. You cannot turn left. A little bit later, this light will change to an arrow here to turn left, and then this one, I guess, may or may not be on to turn right. I don't know. You also see the red here of don't walk, but you can't really make it out very clearly. And that's a don't walk sign because, of course, there's cars turning right. But when you get up to the intersection, the source for this picture reported that almost everyone stops. You don't have to stop. There's a green arrow. You can just cruise right through, turning right smoothly without stopping. So, you have the arrow. There should be no traffic coming. You cannot turn left, however. So that's a little odd, right? And no one really understands that. It's just not a very good design. Okay. We're going to shift gears a little from some of the examples, pictorial examples, to sort of some general examples and then sort of some theory. So the idea here is prevention of human error just common sense? Is it really all about just, well, duh, don't do that? Or is it about something that you can never prevent? That people are going to make mistakes, they're random, you can't predict them, right? We've had this discussion a few different times over a couple of the courses the last couple of semesters about where our role really is in this kind of thing. You're an engineer. You're designing things. You're evaluating things. You're proposing solutions. Where is your role here with regard to prevention of human error? Well, one of your roles is to understand that there are population stereotypes. Whether those stereotypes are correct, in other words, there's a right way to do it, or whether it's just habit, it doesn't really matter, to be honest with you. Is it correct? Is it the best optimal thing to have the the accelerator in your vehicle on the right pedal as opposed to the left pedal. Is it correct? Well, I don't know if it's correct or not. Maybe there's been a study or maybe there hasn't, and I'm not aware. Either way. But I tell you what, if I just decide, you know what's more correct is putting the brake on the right and the accelerator on the left, because you hardly ever slam on the accelerator. You usually slam on the brakes in an emergency, and since you use your right foot, it would make sense to be on the right side. Just logical, right? Okay, if we're going to do it, it's going to be a safer car, blah, blah, blah. What do you think is going to happen when, even no matter how many commercials or training sessions or driver's ed you have that say, gas on the left, brake on the right, don't forget, what happens when you get an emergency? If you're used to driving the other vehicle, you're gonna switch over to where you think the brake is, and lo and behold, it's gonna be the gas pedal. And many, many accidents will ensue because that's a population stereotype for anyone who's experienced driving, and probably anywhere in the world where vehicles exist. Now, that doesn't mean that every kind of vehicle has that setup, right? But your typical on-the-road automobiles do. Here's another set of stereotypes, right? Light switches, and I haven't been to Europe, so I can only know from, I guess, stereotype that this is sometimes true, that here in the U.S., for a single room light switch, where you don't have like 2 or 3 switches that control the same lights, up is on, down is off. Well, in Europe, it could be backwards. Certain places, down is considered to be the on button. And there's no right or wrong, right? That's just convention, just a stereotype. Same thing with water faucets. Counterclockwise is typically on, although it's not as universal here in the U.S. I've frequently found places where I'm trying to turn on the faucet. It's hot water, and it's a little hot. Let me turn the hot water, reduce its output, and I turn it the wrong way, and it scalds me. That's happened quite a bit. The same thing with which side is hot and which side is cold. Now, some faucets, of course, have color coding, red and blue, or an H and a C, but it's not a guarantee, or it's not always visible or easily noticeable when you're doing things. And there's more than just the 2 knobs nowadays. You have kind of the single lever handle that goes left to right. And at my house, when I moved in, I was so frustrated because, okay, so you have the lever, right? It's kind of something like this. Let's see. I'm trying to see where you can see it in the video. And you know that, well, I'm going to pull it what amounts to be to my left, right? I'm going to go to the left with it. Well, I don't know if I can show you in the video, so you sort of need to imagine this. So I pull it to the left, and pull it down to turn it off, or up to turn it on, right? Well, left should be hot, right? Because typically on the left side is hot. But it wasn't in my house. That was cold. I don't know why. And not only that, though, it wasn't centered. It was kind of shifted, right? A little bit. So it was like, so instead of being right in front of me, it was actually kind of turned like this. So I would encounter it, and I had to think, all right, it's shifted a little bit. It's at a 60-degree angle, not directly in front of me. So it's kind of like backwards, front and back. And back should be cold because that's kind of like it's on the right and it's kind of turned a little bit, but it wasn't. Back was hot. So very confusing. All right. What is this trying to demonstrate? This is a classic military example, and it's kind of evolved out of military accident investigations and into most any way of looking at accident. This is not a There are lots more complex and theoretical models for accidents, which we will not go into. But I kind of like this because it sort of illustrates some things that you need to understand. In order for something to happen, an accident, a lot of times people think that we're one mistake away, one small little thing away from disaster. And there are situations where that's true. We call those single point failures. And in a single point failure, what you're trying to say is if this goes wrong, everything's bad, right? If we avoid this thing, it's good. There may be several of those that we have to avoid, but I mean, it doesn't have to be, it's not a multiple set of things that have to happen. It's one thing that has to go wrong. So, asteroids. We're thinking about asteroids crashing into the Earth and destroying everything, right? Either it is or it isn't. Okay, there's, yeah, it's not like there's 5 other things that have to happen. if the asteroid hits us, that's pretty much it. Okay, um, if as opposed to say someone getting a bomb on a plane nowadays. So what has to happen in order for someone to get a bomb successfully detonated on a plane? There's a lot of checks, right? So it has to. You first have to have someone willing to do it, okay, because they're on the plane too, right? And so you're going to get someone willing to do it. So that's one thing that has to happen. But that doesn't mean it's going to happen, right? Now, a bomb in McDonald's here, unfortunately, that's probably a single point failure. If somebody decides they're willing to do it and they get the bomb there, it goes off. But on a plane, that's not there anymore, right? So because you have security, you have the X-ray scanner, right? And you have the terrorist watch list, right? So the idea being you're probably not just going to come up with the idea off the top of your head this morning. You've probably been planning it for a while and having help and that kind of thing. And then you have some other things that I probably don't know about, people that are watching for it or whatever, baggage handlers or something like that. So dog sniffers, I don't know, other systems that I'm probably unaware of. So there's a lot of things to detect that, and any one of them can sort of prevent the actual negative thing. So they all have to kind of line up so that you kind of successfully navigate a lot of fail safes in order to actually, or defenses, we would say here in this slide. You have to actually fail a number of different defenses before the accident happens. But they're not just any kind. You have things called latent conditions and active conditions. Okay. When we're talking about like workplace accidents or things that, that are unintended consequences. So, for example, a pilot, crashing a plane, right? And they say it's human error. Well, what really had to happen there? It wasn't just that the pilot suddenly thought, I think I can make it over this mountain. Oh, darn, I didn't make it. It wasn't that kind of mistake. There are probably a number of things that had to happen. So if the plane crashes into a mountain, perhaps there's a mechanical failure. But that mechanical failure very likely didn't just pop up, right? It probably had been wearing for a while. We would call that a latent condition. It's been there for a while. Or the pilot made a judgment error, but it probably wasn't just a random judgment error. And in hindsight, it's not thinking. It could be a knowledge issue when the wind's really whipping up in a storm under these certain conditions and this particular thing. The pilot just thought this was the right thing to do. From some prior experience or training back in his past or her past, this just seemed like the right thing to do, and it turns out it just wasn't. Right? It just wasn't the right choice. But that's a latent condition. That could have come up any time. It just so happened that the conditions happened to be today. Plus, maybe there are a few other things, active conditions. The air traffic controller didn't recognize the situation time enough to give warning, or there was also a failure of the co-pilot to recognize the situation and adjust, or who knows, right? Some other active conditions were happening, as well as some things, unsafe supervision or preconditions for unsafe acts or organizational problems. All these things kind of were latent conditions, meaning they're present pretty much all the time, and they survive without causing a problem, but they're contributors when a problem does arise due to something active that kind of triggers everything, if you will. So we call all this the Swiss cheese model of accidents. And I bring this out, not that I really want you to memorize this or anything. I bring this out because it's good to think about how things have to kind of line up just so all the holes kind of line up perfectly. Maybe not perfectly, but pretty accurately. And a number of things kind of have to get triggered, sometimes with lots of active actions all coming together at the right time. But other times there's these latent conditions in the background that are okay on their own, but if there's an active thing that sort of triggers them, and it all kind of goes up. So you sort of have to think about all that when you're thinking about preventing things. And a lot of times it's this human error that is just the active condition. It still wouldn't have alone caused the incident. And so all these latent conditions contribute with that active error being made that makes the disaster happen. And so sometimes blaming things on the human error is, even if there was an error, and even if without that error it wouldn't have been an accident, it doesn't mean that that's the main cause, though, because also without all these latent conditions, even if the human made a mistake, there wouldn't have been an accident. So sometimes when we hear that human error was to blame, it's an easy scapegoat, because quite often in some major problem, the human who made the error isn't around to take the blame. Not always, but a lot of times. That doesn't mean there aren't latent conditions that good engineering could have prevented, so that when that human made the mistake, it wouldn't have been a disaster. And that's where we come in. That's how I want you to answer the question, where do we come in this picture? So it's about time. We've been doing this for half hour now. We might as well give you a definition for what human error is. So human error can be defined more than one way. This first definition is a pretty good one. I like it. It's an inappropriate or undesirable decision or behavior that reduces or has the potential to reduce effectiveness, safety, or performance of a system. Apologize, there probably ought to be a closed parentheses there after reduce. There's a lot there. Inappropriate or undesirable decision or behavior. So suppose it's a decision made, a judgment made, or a decision. It can be both inappropriate or undesirable. So inappropriate meaning it kind of violates the norm. Okay, so that kind of implies we should probably know better. Maybe the person does know better, maybe they don't. Undesirable could be that there is no level of appropriateness, but in hindsight, that was not a desirable thing to do, right? So it's not that it was inappropriate, it's just that it didn't work out in a desirable way. So its effect was undesirable, if you will. So we say it's a decision or behavior. So sometimes, it's mental, it's cognitive decision that we're making. Sometimes it's some behavioral thing, and that behavior could be based off of my decision making, or it could be accidental. I don't decide to trip, right? But my behavior is still tripping, right? I still trip. So anyway, both of those decisions and behaviors are involved, and sometimes both at the same time. Sometimes it could be either one. The same thing with inappropriate or undesirable. So sometimes we kind of know in advance, oh, that's an inappropriate action, or even looking back on it, we're like, that should have been easily determined, or even not easily, but we know that's not an appropriate way to act. But sometimes it's just the action itself doesn't have any negatives associated with it. We just look back in hindsight and say it just didn't lead to anything we want. That would be an undesirable action. And how do we know that all these things are true, inappropriate, undesirable? Is that it reduces effectiveness, safety, or system performance. Okay? So it can reduce any of those things. So human error doesn't always have to lead to an injury or an accident. It can lead to some lack of performance in some way. So system performance is reduced because we made a bad decision. I'm an airline pilot, and I did this, and that meant that the flight was 30 minutes delayed. Okay, nobody got hurt, but that's bad performance, or it means that maybe in a pilot situation that wouldn't be true, but maybe it's in my mini Baja car, right? We made a decision, and it turns out that we could only go 50 miles of the 60-mile track or whatever it is. We just run out of ability to perform any longer, so our effectiveness isn't as good as it could have been. All right, we were able to handle the 3/4 of the jumps, but the bigger jumps we just couldn't handle, etc. So anyway, I'm just trying to come up with some examples here. So this is one definition, and I like this one because it's pretty broad, but it is kind of specific in certain ways. Like, it's pretty detailed, I guess. This one is also broad, but doesn't have a lot of specificity. A human decision that exceeds system tolerances. Okay. In other words, I make a choice that goes beyond whatever system I'm in can handle. All right. So I choose to pull up the plane at 80-degree angle, and you know what? This plane just can't handle that, and it stalls, and we crash. Okay. It's human error. I made a decision, but that decision couldn't be backed up, if you will, by the system I'm working in. And that system could be anything. It doesn't have to be a mechanical system. It could be a personnel system, right? It could be a football team, right? I decided to, run a 80-yard post, and my quarterback can throw it 30 yards, right? The system I have, my decision to do that did not. The system could not handle that. Okay, we were not there. All right, so we threw a duck, and lo and behold, it was interception, and we lost the game. Failure to achieve the intended outcome in a planned sequence of mental or physical activities. I don't like this one as well because it's outcome oriented. You can have human error, but without necessarily always having some major catastrophe, But this is kind of a way of looking at it from the outcome point of view. So instead of looking at it kind of from the top down, this is looking at it from kind of back the end of the system, looking back into it and saying, did we meet our objectives? Did we have the intended outcome? If we did not, and it was in a sequence of activities that were involved the human, then it was human error. Okay, see what I'm saying? That may be overstating it a little bit, but I kind of like the fact that it depends on, well, did it work? Did the system work the way we wanted it to? It did not? Well, there must have been some human error somewhere in some activities somewhere along the way. All right. I guess that's kind of, I wouldn't say that's always true, but it does give you a different perspective on looking just to see. I start at the end and I say, well, there were problems, so let's go back and find where the sequence of mental or physical activities broke down. Okay. This chart illustrates some pretty old data, but it's still kind of interesting. So this is like 30-year-old data. But the idea is looking back on a number of significant accidents or events of some kind, more than 400 of them. They wanted to see what were the primary causes. And you can see that human performance was attributed as the main cause of this big negative experience more than half the time. Then design deficiencies, another third of, well, 2/3 of what was left. And then this other little pie wedge here, about, what does that add up to? 15% or so, are manufacturing defects, some external thing, act of God or whatever, or even unknown causes in there. So the point being that human performance, judgment, physical capabilities, etc., failures of some kind in the human part of the system, more than half of the causes. And then you say, well, there were design problems. Well, duh, who did the design? That's probably also people, okay? So really it's 85% of the primary causes were seen to be human related. And frankly, since humans are involved in everything, that's probably not a surprise. I mean, we don't have robots building these things, or the system's just evolving out of thin air, right? We're always involved, so of course we're always part of the problem, pretty much always. Okay, shift gears a little bit to some theory. So you probably are familiar with this from maybe prop stats, I would say. You didn't probably call it signal detection theory, okay? But still, it's the idea. You might call it type 1, type 2 errors. Same idea. Let me just frame it for you, though, from a signal detection point of view, information processing. So this is kind of a classic cognitive engineering way of looking at things. So you have some information that's a stimulus to your senses. In other words, you're perceiving, I just perceived some information. Two things can happen. You can perceive it, or you could not perceive it, right? And perception is, it kind of involves recognizing it correctly, etc. So suppose that information is a warning of some kind. You're the airline pilot again, and it's saying, all right, I have engine failure, right? So what happens? Well, the engine failure warning comes on, and as the pilot, I recognize it, and I say, yes, there's an engine failure. If that's correct, that's here. That's called a hit. There is a signal, and the operator responds appropriately, recognizes it and responds. That's a hit. Just exactly what we intend. The opposite is there is no signal, and the operator correctly realizes there's no signal. So in other words, the operator does not respond. So the operator does a check to see if there's a warning light. There's none. And the operator says there is no warning light. That's called a correct rejection. In other words, I correctly recognize that there is nothing, there is no signal, there is no issue. But it's the other two categories where we have problems. What happens when there is a signal, but I, as the operator, do not see it or do not recognize it appropriately or decide to ignore it or whatever? That's called a miss. A miss is when there is a signal that I do not perceive. Okay? The other side of that coin is What happens when there is no signal, but for some reason I think there is? We call that a false alarm. It doesn't matter if it's an alarm or not. It can be anything. This can be a cancer screening. So you go to the doc, right? And you either have cancer or you don't, right? Only two outcomes. But four things can happen, right? You can have cancer and the screening can catch it. You can not have cancer and the screening can say you don't have cancer. Those are, we don't like to have cancer, but those are the two correct things to happen. If it's there, we see it. If it's not there, we say we don't have it. Unfortunately, you can also have cancer and miss it. And that's sad because then it's not caught. Another thing that's maybe not as sad but still troubling is you could not have cancer at all, but the test could come back and say that you do. Imagine what happens there. You think you've got cancer. Oh, no, I've got cancer. And you go through all the treatment before it's finally caught that, oh, in fact, you don't actually have cancer. Sorry about that. Our bad. Right, false alarm. Okay. Now, those are the four categories, and I really want you to know those four things using this terminology: hit, miss, false alarm, and correct rejection. All right? Which ones are good? Which ones are bad? Okay? We like the green ones, hit and correct rejection. We don't like false alarms or misses. Now, unfortunately, how do we handle that? When we're designing things, when we're evaluating things we need to recognize, well, is this system set up to minimize the misses and the false alarms? Well, guess what? It turns out it's actually pretty difficult to minimize both of those things, to maximize the hits and correct rejections and to minimize the misses and false alarms. I'll illustrate with that cancer screening again. So how do I minimize false alarms? What's the best way to minimize cancer screening false alarms? Well, remember, a false alarm is telling you you have cancer when you don't. What if I tell everyone they don't have cancer? I don't even check. Anybody a Battlestar Galactica fan? Right? The Baltar invented a Cylon tester, and he was just going to tell everyone they weren't Cylons, and lo and behold, he found one. But he wasn't going to say he found one, so nobody's a Cylon. We're all good. Okay, nerdiness turned off now. Cancer screening. You can walk into my clinic. I can screen you. I can have a test that I've got a tissue here. I'll wipe your forehead, look at it. I don't see any cancer. Cancer screening says you're good. I'll never have a miss. I'm sorry, I'll never have a false alarm. I will never come up in that system saying you have cancer when you don't. You'll never go through the idea of falsely believing you have cancer and receiving treatment and all the expense of that. Now, unfortunately, I will never catch any real cancer, which means you probably will die from cancer if you have it, because I will never catch it. See how there's a trade-off between misses and false alarms? So what if I never want to miss? Well, I can design a cancer screening that always finds it, okay, if you have cancer. Now, it'll be darn expensive, and I'll probably have to cut you open every time you come to see me and check every organ, and you'll probably die on the operating table from all that surgery. But I can do it, and by golly, we'll never miss cancer. Now, for all the people that don't have it, getting every one of your exploratory surgical procedures done for every major organ is kind of annoying. But we'll never miss it, right? These are very extreme examples. I get that. And usually we're well in the middle of that category. But there's that trade-off. You have to think about it in your system. What happens if there's a false alarm? So, if we're looking for bombs on airplanes, what happens if there's a false alarm? We land the plane, everybody panics. Oh, false alarm, wasn't really a bomb on the plane. Sorry. What happens if there is a bomb on the plane and you miss it? It blows up, air traffic is stalled, we have a new war for 13 years against the country we think did it, right? Okay, that's also bad. So where's the fine line? Where do you design the system so that there may be errors, right? You might miss something that's there, or you might falsely think something's there when it's not, but you can live with that the best you can. You got to find an optimum, and that's not an easy thing to do. But it's definitely one system or the other. It depends on what your system criteria are and what the costs are and what the consequences are, and you have to work all that out. Okay, this is just kind of a framework for understanding it, really. So what do we do again as engineers? Well, we want to maximize hits and correct rejections. We want to minimize misses and false alarms. Here's a few ways of looking at it. False alarms are quite often expensive, all right, because you have to act like they're real until you find out for sure if they're not. Again, think about the bomb on the plane thing. How expensive is it to, oh no, we've got a false alarm. I'll tell you a story I had not very long after September 11th. I was taking a friend to the airport in Atlanta, and I'm driving there. And it's about an hour and a half drive from where I live, so I left and everything was good. You know, this isn't before the days of smartphones and apps, so you could like constantly keep up to date with your flight schedule and everything like that. So, you know, you check in online when you leave the house, and it's good. And so, you know, you assume it's good. Well, in that hour and a half, some idiot decided that he went through security and he forgot something, went out to his car, decided that security line was really long. I've already been through security. I'm just going to skip it. And he decided to skip security. And he walked through the do not enter side and wouldn't stop and was running late and was going to miss his flight. And guess what? Airport shut down, flights are grounded, tackled the guy, security alert, calling the bomb sniffing dogs, evacuate the airport. And all that happens while we're gone, and and we get there and we're like, there's like thousands of people standing in the parking lot. You can't get in and out. So we were smart and we went to one more exit up the interstate from the airport where there was a public transit train that drove to the airport. Got on the train for $2, rode into the airport, dropped itself right inside just as the airport was reopening, walked right into the security, and out we were. And everybody else was looking at us through the windows. Why are these guys getting to go? Well, they just opened the train entrance first for some reason. It was kind of great, actually. Anyway, but that was extremely expensive. That was an extremely expensive false alarm. The person was just an idiot. Wasn't actually dangerous. Now, misses can be dangerous. If instead you miss the 9/11 hijackers who safely make it through security with their box cutters and the other things that they hijack their planes with, you know, we know what happens there. All right. Signal detection theory and VMITs. Let me tell you what a vigilance, monitoring, and inspection task is. These are very cognitive intensive operations. Okay, my examples here: security guard, power plant operator, quality inspector. These are things that you're working with your brain, your eyes, your senses. You're not really necessarily using your physical abilities to move things around all the time. It's not material handling really. These are tasks where your brain is active for the bulk of it, doing making decisions, recognizing things, determining whether what you're seeing or perceiving is needs a response or not, etc. So, and there are three different kinds. And I do want you to know the difference here. So a vigilance task, this is like a security guard, requires constant sensory processing. I'm constantly with my eyes open and my ears open, even my nose open, right, smelling for things. I'm constantly trying to determine if there's some kind of threat or something I need to do, and I don't even know what that event might be. I have some ideas, but I'm also looking for the unknown, right, for the abnormal thing. So it requires constant processing of data, and you're unsure exactly what the event might be. You don't know exactly where to look or what you're looking for. You're just looking for something that you perceive to be needing a response. And then the non-events, the things that you don't respond to, you're just sort of think of as normal. Okay, things look normal. All right? They're undefined non-events. It's not like you flip a coin and on tails you don't do anything and on heads you do and you're looking for tails or heads, right? It's not that cut and dry. It's unknown events that you respond to and just sort of the normal, everyday non-events that aren't very well defined either. You just know they're normal. All right? That's a vigilance task. The name implies that you are constantly active, right? There's no rest. Okay, you may not think of a security guard, a mall cop, or whatever as being a hard job, but that's because you're not thinking about what the sensory processing requirements are, right? You have to be on it all the time. Doesn't mean everybody is. That's just what the job requires. The other, or the middle kind here, monitoring tasks. This is like a power plant operator or someone who's has specific things they have to look for. So constant processing of sensory data, right? You never have a time off. It's not like, all right, every 30 seconds I'm going to look at this screen or something like that. You're constantly taking in information pretty much all the time, but you're usually looking for some well-known events, right? You're watching to see if the gauges hit the red, or you're watching to see if, the reaction at the power plant is going appropriately, or, whatever it is, or any other monitoring task. The casino um, security in watching all the videos, right? I've got the blackjack tables. I'm watching for somebody counting cards, and here's what I kind of think that looks like, and I'll let the boss know if I see it, right? That's a monitoring task. You're always watching, but at least you know somewhat what you're looking for, usually pretty specific things. Again, though, the non-events, the normal case, there's a lot of that. It's undefined. There's not just a few normal. There's tons of things going on that are considered normal. There's just a few things you're going to look for that are responses that you need to make. That's in a monitoring task. And then last, an inspection task, like a quality inspector. This is someone who's knows when it's time to turn on their senses. So maybe you're supposed to select every 10th part off the line and do a quick inspection of the welds, right? So you don't do the other 9 parts. All right, here's my 10th part, I'm going to grab it. Or maybe it's a random grab. You just go and you grab one. You look, for a few seconds, you put it down, and then you're turned off again until the next part, until the next time to do it. Now, it's not that you don't do it quite a bit, but it's not constant. You have kind of the on time when your senses are operating, and then you have the off time when you're just waiting to the next one. And that's an inspection task. And this is also looking for very well-known events. Like, what it looks like when the weld isn't right. Right? You're trained, oh, this weld has a defect. You know what you're looking for. Non-events are also well understood in this case, so that's a big difference here. So there's no constant processing of data, and what the correct case looks like is also, okay? This is kind of the coin flip almost, right? All right, every time there's a coin flip, I'll look, and if it's a heads, I'll act. If it's a tails, I won't, and I know what it looks like. Or maybe it's a die roll, and 5 out of 6 times I'm not going to do anything, but, if I roll a 6, then I'm going to act, right? You know what the non-events look like. You're inspecting fruit. You pick up the nice round orange-colored orange, or you get a discolored orange, right? You know both cases. You've seen them before, and you know what you're looking for. So there's a few slides here that I want to go through, and I'll go through them as fast as I can, that are design recommendations for these vigilance, monitoring, and inspections tasks. So first, you have saliency. Saliency is the intensity of the signal. It's making sure that the signal stands out from whatever other signals are in the environment. So if I'm going to design a fire alarm, right, and I don't want it to sound like a cell phone, because I hear cell phones in Surbeck going off 3 or 4 times every time I walk through there. If that's what the fire alarm sounded like, it's not salient. It doesn't stand out. It can be ignored, or it can be attributed to something that's not what it's intended to be. Okay, that's saliency. So you definitely want to make the signals that they need to recognize as salient as you can, right? So having a static field monitor where you've got just a handful of pixels that are active trying to find the bank robber, as opposed to a nice HD TV, really color, so that when somebody whips out a weapon in the bank, you immediately recognize it, right? That's another attempt at saliency. All right, persistency. Persistency and consistency are very similar. I'll try to elaborate on them, okay? Best thing to do is just kind of remember the bullets I have here for them. Persistency is letting the user kind of control and know what's coming. So when we say keep the task stationary, what we mean is, so if I'm an assembler, right, and or say an inspector, right, and I'm inspecting parts, looking at those welds again, keeping the task stationary, that means that I don't sometimes send them in boxes that I have to unpack, and other times they're individual, and sometimes they're stacked on each other, and sometimes they come with the parts attached, and sometimes they're not, right? That's, let's be persistent at the fact that I can do the thing that I do, right? And I don't have to, but I am in control of how often I do it or when it's appropriate, right? So if I need to take a break, I can. That's called persistency, and that's not a great name for it, and I admit. Consistency, is similar, but consistency is basically saying, if I'm going to be inspecting 3 welds, I want to be able to pick up the part, spin it around, spin it, set it back down, and always it's in the same orientation, right? I'm looking for the welds in the same point, right? They always start and finish in the same place, so that I always kind of look for where that happens so I can recognize them. It's not some hodgepodge random Rubik's Cube situation that I have to treat everything differently. All right, now let's find the welds on this piece, and now let's find the welds on this piece. Who knows where they are, right? Everything's done very consistently, and it's presented to me very similarly so that I can get into a routine. And that's really what both persistency and consistency are about. If I get into a routine, I'm not spending my cognitive resources, my limited resources, on understanding how the information is going to acquire. I can just concentrate on the information I'm looking for. So that's what we're doing there. We're decreasing the cognitive load by making things persistent and consistent. And that's engineering. We do this. We set that up, right? Simplicity is probably obvious to you if we're trying to minimize cognitive load, but we're just minimizing the number of stimuli. Both how many things come up, right? How many things I have to watch at the same time, but also what am I looking for from each signal? So, if this light that flashes on can be yellow, green, red, blue, orange, flashing red, flashing orange, or off, that's a lot of things to look for one signal, right? Can I just make it on or off? Do I really have to have all those different things? Can I look at a screen when it comes on to see or read what it's, what the problem is? Do I have to memorize all those different kinds of lights? It's kind of like the old weather sirens. Here we just have one siren, which is good. The old weather sirens used to have, or you had the short, which was different than the very long, and then it was 30 seconds or 3 minutes. You sort of had to keep track of how long have I been hearing this, and then and they were all for different kinds of events: tornado warning, severe thunderstorm warning, flash flood warning, and all these things. And they realized that if there's a severe thunderstorm warning or tornado warning, do you really need to know the difference right now? Can you just know you need to go to the shelter? Do we really have to know whether or not it was hailing and straight line winds, or whether there was a tornado, right? So they took that away in most places. Simplicity. All right. Pace. This is, when we talk about pace, what we're talking about is how often a signal happens. This is kind of a simple rule of thumb here. If whatever you're looking for doesn't happen at least once every 3 minutes, that's 20 times an hour, your boredom will often cause you to miss when it does happen. So if I'm looking for something that happens 2 or 3 times an hour, and I have to stare at this screen until it happens, I mean, imagine how boring that would be. Every 20 minutes, you're like, okay, I finally saw one. Do you really honestly think you're still staring at it, 40 minutes in, you're not going to miss when the signal happens? Okay, so there's this concept of artificial signals that a lot of folks will use in these kind of tasks. If the actual thing you need to see really is infrequent, less than 20 times an hour, you need to put in some artificial signals, some all clears or whatever. And you'll hear this, dispatch will do that for like, transit system, train operators, or whatever, right? They need to make sure that when there is an issue that you recognize it, but just to make sure you don't tune out, right? We're going to essentially say check in every so often, every couple minutes, hey, check in, tell us where you are. These are not necessarily that important, but they keep the channel open, so to speak, to make sure that when I do get a signal coming in, I'm going to see it or I'm used to responding, okay? So you just don't essentially get bored. Just imagine staring at a screen, waiting for something to happen for 15 minutes and nothing ever happens. Are you really going to see it at minute 16 every time, right? No. Anticipatory cueing is essentially kind of a pre-signal, okay? You know when the signal's coming, right? One example of that is the emergency, what is it called? This has been a test of the emergency response system, or whatever it's called, the national emergency. You have the signal. Do they still do that signal on the radio? I don't remember. Or on airwave TV, right? The idea is getting you used. That's the cueing. You never actually get the warning signal because it's almost always a test. But it's getting you used to the idea that if you hear that signal, expect that there's a really good information to follow. Okay, that's the idea. There's lots of ways to do that. You sort of know it's coming, right? And then it sort of gets your attention, and then you see the signal. Feedback of accuracy. Okay. What do I mean by that? What I mean is, well, knowledge of results. What we're saying is, I need to know if I correctly saw the signal, if I judged it right. Was it a mistake made or not? Because it helps me make adjustments. So if I'm the security guard and I'm looking for the bad guy, right? If I call it in, all right, I think I see a person out here on the sidewalk that looks suspicious, and I never find out what happens from that. I never know if I should continue to look for that suspicion or not, right? So if I get some feedback from the police, oh, we checked it out, it was just some dude walking around, no big deal, then I know, okay, maybe I won't be quite so suspicious of that next time or something like that, right? Knowledge of results, also called feedback. Environmental quality, this is just saying minimize distracting signals, noise. We would call that noise whether it's an audio signal or any other kind of signal. We don't want distracting things. If it's hard to get past the background noise to recognize your signal, right? That's a saliency issue, but you can do it both from the signal design point of view, but also from the environment point of view. Can we lower the background noise? So it's kind of the other side of the saliency coin. Make the signal as salient as you can, and then minimize all the background noise, and that kind of gives that nice contrast when there is a signal. And the last slide here on these things for design recommendations. Training. Practice obviously will help in these kinds of VMIT tasks. Okay, you don't want to put a security guard out there with no training. You don't want to design some kind of inspector who's never been trained on what they're looking for, obviously. But when you design that training, and again, engineers, we do a lot of training. When you design that training, you want to make that training as realistic as you can. The pace, right? In other words, how often I have to respond. I should be in the real time. Like, don't give me, 2 events every 5 minutes when in the real world it's 2 events every 10 seconds, right? I'm not going to be used to that, okay? Or ratio of events to non-events. So if I'm having to learn whether the welds are bad or good, and really the welds are only bad, once in 100 parts, then give me 100 parts and let me find the one for practice, right? Or give me 200 parts and let me find the 2. Don't give me 5 parts and let me find the 2 that are bad, because that's not really training me on how often I need to go before I find a real problem, right? Scheduling. A 5-minute break every 30 minutes will minimize misses. Well, what does that mean? Misses. Why do misses happen? In other words, I miss the signal. Well, we already said that you get bored. Your arousal is reduced. Okay, arousal is kind of how focused I am on making sure I can perceive the signals that I need to see. About 30 minutes in, a lot of people start to, no matter how vigilant they are, they start to wane in their ability. So a 5-minute break where you can sort of change your scenery. This is not just a sit back for five minutes and stare at the same screen, but you're not on duty. It's not that kind of break, right? This is a get up, change your environment, do something different, refresh all those senses so you can go back and be ready to go again. That usually works pretty well. Teaming. Okay, reliability. This is a really you could study this for ages, okay? You study it in the quality control class probably, but you could also study it in the human performance class. Human reliability, big deal. But in order to illustrate, I'm going to illustrate using automobile airbags. So how many airbags do you have to protect the driver? Well, you've got a side airbag, you've got the steering wheel airbag, right? And I suppose they all have their individual sensors that, so they can go off individually, one at a time, both of them, whatever, depending on the crash. So let's think about just the steering wheel airbag, the front collision airbag. So what makes that go off? Obviously collision, but I mean a collision with an apple. I mean, an apple falls from the tree, and right as it's falling, you run into it. That's not going to make it go off. You don't have to hit a brick wall either. So what is it? Well, there's a set of accelerometers or force sensors or something in there that's going to detect the collision. Well, every sensor fails. What if the one sensor you have that tells you when you're in a front-end collision or not fails? So, how's it going to fail? Well, you think about it in the same way you think about it in signal detection theory. What if it has a false alarm? Driving down the road, false alarm, airbag. Okay, that's dangerous, and that's happened to people before. Or a miss could also happen. In other words, there is a collision and the sensor does not detect it. Right? It fails in that way, and that happens too. In fact, that's happened very recently with General Motors because of some ignition switch issues. It also leads to moving vehicles running off the road, but there's a failure also of the airbag sensor because there's a power issue that causes it to fail. And you hit a tree or a vehicle or something and the airbag doesn't deploy. So anyway, that's obviously a problem. So what do? Well, they don't rely on just one sensor because no matter how reliable a sensor is, some will fail, some of the time. And so what do? They have multiple sensors. Maybe they have 5 sensors or 10 sensors on the front of the vehicle. And they have a set of rules in place. They sort of have a team of sensors. Now, they don't all have to go off at the same time, but we also don't say just one, right? Any one of them, because if you had 10 sensors and any one of them could set off the airbag, what are the chances that at least one of them is going to fail during the life of the vehicle? It's probably a decent chance. So what are the chances of them that 2 of them are going to fail at the same time? Or 4 of them out of 10 are going to fail at the same time? Now that becomes really unlikely. And so that's what it is. We would call that redundancy. Okay, and the redundancy aspect says we require more than one simultaneous reception of the signal to decide that the response is necessary. And that really minimizes false alarms. Okay, if 3 sensors all individually say we're detecting this signal, then there must be a collision around those 3 sensors. Maybe it's a small enough collision that it doesn't activate the sensors on the other side of the bumper, but it's large enough here that we should act, and 3 of us agree that it's happening. We're not going to agree because we came to the conclusion individually as sensors. We're not going to agree unless it's significant, and the probability of all 3 of them failing at the same time are very, very remote. So that redundancy means we have a lot smaller chance of a false alarm. But what about a miss? What are our chances of a miss? Well, what if only 2 of the sensors detect it? Well, I need a 3rd one before I'm going to respond. So what if it's a real signal, but only 2 detect it? Well, what are the chances that out of 10 sensors, 8 of them are going to miss the signal at the same time? There are good reasons that a signal might be missed. Like I said, for airbags, perhaps it's a smaller dent on just one side of the vehicle and the other side sensors might miss it, but still you have 5 sensors on this side, and if only 2 of them are reading it and 3 of them are missing it, maybe there is something there, but it's not very significant, or maybe just it's that 1 in a million chance where those 2 sensors are actually failing at the same time. So by having a 3 sensor or more rule, that pretty much means you've minimized false alarms a lot, and you've pretty much minimized misses, although probably you'll get a few more misses than false alarms. But anyway, there you go. That is an example of how to use teaming. Now think about instead we do people. So what would be a situation? So I have 2 fruit inspectors. And so I detect, I pull out the fruit, and then later on down the line, someone else pulls up the fruit. And if we both let it pass, the chances that we both missed a big brown spot or whatever on the fruit are pretty slim. Or we both missed a bad weld in the, on the part is pretty slim. So that's a lot of times what happens. You'll see that at airport security. You'll have multiple people involved. They're not just one guy or one gal running that thing. They'll have other people who are looking, even if they're not staring at the 3D scanner screen. They're also looking at you, and they're thinking, they're doing this to try to increase the reliability. Then finally, visual aids and samples. In other words, if you're going to, I need to give me a rotten piece of fruit or a drawing or a picture of a rotten piece of fruit so that I know exactly what I'm looking for instead of having to remember it. You know what I mean? That's pretty easy to do. All right. So there's some theory. Now let's move on to a different kind of theory. Okay, um, attention. Attention, right? Your optic nerve transmits 1 million bits per second. Yet your brain only processes about 100 bits of optical information per second. Where does the rest of your optical information go? Well, good question. That's a 10,000 to 1 loss. Okay, for every 1 bit your brain actually processes of visual information, you lose 10,000 bits. It just goes away. It's ignored, essentially. And why is that? Well, processing visual information, recognizing what I'm seeing, processing its color, its shape, what it is, going, activating my memory to recognize have I seen this before, or whatever it is that you do with visual information, takes a lot of attention. And your brain has a limited set or limited capacity of attention. Everyone has a limited attention capacity. All right, it's a resource, just like any other resource that you might use to design things. How many welders do we have? X. How many assemblers do we have? How many drill presses do we have? How much money do we have? Whatever your resources are. For human, attention is a fixed resource. Now, we all have a little bit different values of that resource. Everybody's different, but it's still fixed. Unfortunately, we don't really know exactly what it is. There's not a good way to go and say, all right, I want to know exactly how much attention I have. How many bits can I work at the same time? We don't really have that ability. But what we do know is that some tasks take more attention than others. Okay, some tasks require more cognitive processing than others do. And so we kind of have a relative way of handling this. We don't really know, all right, I've got 63 and this task takes 58, so I've got 5 bits of attention left. It doesn't really work like that. We do know, though, that when that capacity is exceeded, when we are asking more attention of you than you can give, that we see a dramatic increase in problems. Mistakes, primarily. Mistakes, or just ignoring things, or trying to juggle things you can't juggle, and neither performance just really suffers in both or all the categories you're trying to juggle, etc., etc. In order to detect a new signal, right? If I'm doing something, so I'm a security guard, I'm watching my video, but the boss has said, you know what, this guy sits around and watches TV all day. That's not very good. Let's give him something else to do. Well, how do I know I'm going to have enough attention free to detect when the real signal happens? Or maybe more likely, the person is just watching TV. There's a really intense football game on, and I'm really watching and watching. What are the chances I'm going to actually see when the signal happens? The point being, I've got to have free attention that I can allocate to a new signal. Now, I can free it up by withdrawing it from something else, or I can free it up because I'm just not using it for anything. So you have 3 kinds of attention. I'm going to hit these fast because I want you to kind of know what they are, but it's not that big a deal. Selective attention requires attention switching. So this is, I've got a lot of things going on, and I'm supposed to focus on one. It's kind of single task way of doing things, right? One-track mind, and everybody always jokes guys are a lot more one-track minded. I know I am personally, so for that reason I probably believe it. So when I need to devote that attention to something else, I have to turn this off and turn the other on. And so you have to have very different stimuli because I have to kind of recognize, all right, this very different thing now requires my attention, so I turn this off and turn this on. Divided attention is kind of multitasking, okay? I'm terrible at it. Most people really aren't very good at it. Some people can do it okay. Even then, though, one task is usually primary. Here's my main thing, and I'm kind of doing some things on the side as well. As long as they're not simultaneous responses required, right? I have 2 very different signals that pop up exactly at the same time and both need a response immediately, and there's no way I can do 2 things at once, etc., etc. Then you can do this okay with well-designed. So one primary task that requires a little more cognitive load, and maybe the other things are kind of background tasks, and occasionally they come forward and you need to address them, and you put the other on the back burner, but you're monitoring kind of constantly. All right. And then vigilance. Again, we've already said you need attention for a very long time looking for something that's hard to find, it's rare, and you don't know exactly when it's going to come. These tasks decrease arousal. In other words, your response time to when the signal happens can be an issue. Now, both low arousal and high arousal are bad. I don't want to be hyped up. Or, oh, I'm crazy. I'm on Red Bull or whatever. Right? High arousal also doesn't necessarily respond very well to signals, but very low arousal. Oh, this is boring. That is also bad. So one thing you can do to kind of limit arousal from decaying and becoming too low is to, have different kind of signals. Have an auditory signal, a visual signal, and you have those kind of artificial signals to keep you aroused, right? And then rest. Rest is the best way to recover arousal. And, give an hour a break, right? Go take a nap. I don't know. Find some way of recovering. What I will say about this chart is, well, first of all, the chart itself is like a walking, well, not really walking, I guess, a very good example of bad design for human error. So, for example, you have 1s, 2s, and 3s in this chart without looking at the key down here at the bottom. Okay, don't look, don't read it. I know it's going to be hard not to read it, but don't read it. Tell me what we're talking about. Common errors for given tasks. That's the name of the table. So, control and display tasks perceived when not there is a 2. Not perceived on time is a 1. What does that mean? Is a 1 worse than a 2 or 2 worse than a 1? Well, what this is actually saying is this is the likelihood that this type of mistake is going to happen in this type of task. Okay, these stages of mistakes happen in each of these tasks with some likelihood. The higher the likelihood is a 1, the lowest likelihood is a 3. So a 3 is not very likely. A 1 is extremely likely. Okay, your main focus. So see, that's not a very well-designed table. It also kind of helps you when you have a different type, like assembly, right? What are you looking for? Well, time can be an issue, right? Not understanding things are not really an issue. You're not going to misunderstand something in assembly very often, but you might not perceive it at the right time. You might miss something just from a time point of view. But down here, again, timing wrong or incorrect action, you leave something out, you add something, or you replace something that shouldn't replace. That's definitely a major concern of assembly, right? You want to get things in the right order, in the right sequence, right? So that's a primary error concern. Physically incapable of performing it, well, if you're in an assembly job, that could be a problem, but most of the time that's not going to be a problem, but it could be. So that's a 2. Do you see how it works? All right. I'm going to be quick on this slide as well. 2 kinds of error. Design error and operator error. What we mean is both things are human mistakes, but is that human mistake happening when the product or system is in use, or is it happening way back on the design floor, okay, when it's still being designed? So did I make a mistake in the design of it, development of it, testing, etc., or did the operator perhaps make the mistake? I don't know. Both of those are human error. I would say that when you hear on TV, when there's an accident and you talk about human error, it's almost always operator error. You very rarely hear it called human error when it's talking about some designer somewhere blew it. But perhaps on a bridge, if a bridge collapsed, right, and they call it human error, that would be a design error, obviously. All right, this slide is really important. I want you to remember it, okay? I want you to at least remember these yellow boxed terms. So, what are we dealing with? Well, when you're talking about error, you have 2 kinds. You have the intended and the unintended. The unintended actions are things that happen obviously by accident or at least not on purpose. This could be failures of attention or failures of memory. So a slip is when my attention fails. Okay, we're not talking about a slip like if you slipped on the wet floor, although maybe that's an attention failure, I guess, if you don't recognize that there's floor there, that's water on it. But this would be if I'm driving down the highway and I know I need to take exit 57 and I just get distracted. I'm listening to a song, or I'm complaining about the traffic, or I'm reading the road signs, or I'm just, driving. And Oh, darn it, there went my exit. I missed it. My attention was off and I didn't recognize it or perceive that the exit was available. All right. Sometimes we'll say, I forgot. Oh, I forgot to take the exit. But it's not really forgetting. It wasn't my memory that failed. I knew which exit to take memory-wise. I just didn't recognize when it popped up at the right time. Okay. My GPS didn't tell me or something like that. Right. So that's a slip, right? My attention was directed elsewhere and I didn't recognize the thing I needed to do. It wasn't intended. I didn't mean to do it, but it's a slip. A lapse, that's when I forget. So that's when I'm driving and I'm like, which exit was I supposed to take again? I think it was 55. And so I take 55 and I get to it was 57. Darn it, I forgot which exit. I took the wrong one because of a memory file. I just forgot which exit again was it, and I took the wrong one, okay, or I missed it. That could be a memory where you just don't remember what it is, or you remember it incorrectly. You know, my account number on my on my checking account, right? And sometimes I still throw in my way old account number that I memorized 10 years ago because it's in my memory and I can't memorize my current one very well. And I spit it out. And I'm like, oh wait, that's the old one. Right? That's a memory failure. We call that a lapse. Those are the unintended errors. Intended errors. Now there's actually more than one. A mistake. That is when I think I'm doing the right thing, it just turns out I wasn't. Okay? That's when, that's not a memory failure. That's not because I forgot. That's because I worked it out and I'm like, you know what? I think that taking exit 55 will get me to where I want to go on time. And taking exit 57 will not. And I take exit 55 and I'm 5 minutes late because it was slower and I got caught in traffic and there's more lights and, well, I guess I was wrong. A lot of times that's how we would say that. I'm wrong. So we might say that, a memory failure, a lapse, I didn't remember it correctly, but this is where I just judge it wrong. Or my knowledge is incorrect. This is training, right? So I think I'm trained in how to drive. You're supposed to, or you don't have to put on your turn signal when you're changing lanes. And I think that's correct. It's not. Okay, it's a mistake. All right, so my choice of making the action, I do it deliberately. I'm not right. The other intended action is a violation, and that's where it's not that I'm wrong in the sense that of what I think. I know it's incorrect. I know what I'm doing is incorrect. I just do it anyway, right? I think I can get away with it, or I actually want the negative consequences to happen. So, I rob a bank, right? That's a violation. It's illegal. But I also could just take off a safety guard. And then when I cut my hand on the spinning saw blade and the guard was removed, it's not because I forgot to put it on. It's not because I thought it was okay to have it off. It's not because I didn't recognize when I walked up that the guard was missing and I just didn't see it. Okay? It's because I didn't like it. I didn't want it on there. Okay? That's a violation. All right? There's a little bit of overlap maybe between mistake and violation, but not really. I think you kind of know the difference between when I think I'm doing right and I'm not, and when I know I'm doing wrong. You know what? I'm going to skip this slide. It's informative, I suppose, but not really for our class. Why is it hard to detect errors? What makes it so hard? Well, we have expectations, right? We all think something is going to work. I don't know in advance that I forgot something, right? Well, I guess sometimes you do. Sometimes I'm walking around going, I know I'm supposed to do something, but I cannot remember what it is. Sometimes. But most of the time, I don't recognize until after the fact that I've had a lapse or I've had a slip, right? I mean, you certainly don't know that you're not attentive to something. Or you have expectations, right? We all talked about the stereotypes, the populations, and we're all different, and we don't necessarily know whose expectations are different from whose. I can't look at you and know what your expectations are, and it's kind of human nature for me to assume that you're similar to me when it comes to your expectations. Sometimes cover-ups. In other words, it's hard to investigate and really get and figure out where the errors happen so that you learn from them, because nobody wants to acknowledge they made a dumb mistake. Oh, I just had a slip, right? So we like to blame it on other things, or it's minimized at least in some way, or it's hard to get information about it. So it's hard to really evaluate it honestly. And a lot of times it's a communication issue, right? So why would someone have knowledge-based issues? Why would they make a mistake? Well, because there was bad training, okay? Or because they learned it differently, or people didn't recognize when their behavior had suggested that they had a poor understanding of how they were supposed to act, et cetera, et cetera, et cetera. And the communication just wasn't there. There were people that knew how to do it. It just didn't transfer, or it didn't happen, or we didn't recognize it, or we didn't talk, or right. It's really easy for each individual person to have their own thing, and then the intercommunication between people is where the problems really arise. This is just some ideas. This is not a list or anything like that. I just want you to think, why is it hard to detect in advance error situations, or difficult at least to detect them? Everybody thinks like me. I have different backgrounds and judgments, and I've evolved the way I judge things and recognize, perceive things based on my experience that no one else has, or my background, right? And it's hard for me to even realize that's why I do what I do. Look at these signs, right? So this is an airport, international airport here. Which way do you go for the exit on the top one? You go down an escalator, or do you just go straight? It turns out you just go straight down this little straight moving path. Well, you can't see all of this one, but up here, arrivals, is it straight ahead, or do you have to go up? Well, it's straight ahead. Different airports, different languages perhaps, different arrows both mean go straight, right? Different population stereotype. Down is straight, up is straight, right? And neither is really straight, right? We just gotten used to that in a two-dimensional sign. And here's some, just don't worry about this slide, just for your information, I guess. Can you spot the problem? Well, a couple of good examples here. This door, right? It's got a lock on it, got a handle. You pull the handle, and you go out onto this little breezeway between two buildings. And you pull the handle, and it opens. And it closes behind you, and you hear a click. And you're like, uh-oh, maybe I should have figured out if the door locked from the outside. And sure enough, you try, you pull on it, and it doesn't open. Well, darn. So then you go over to the next door, and there's no lock visible because this is the outside of that door. And you pull on it, and it doesn't open. And you're like, oh crap, both of these doors are locked, and now I'm stuck in the breezeway. And you get on your cell phone, and you call, and finally your friend comes up, opens the door from the inside, and it opens. And you think, well, that's because, well, it just locks, but you can open it from the inside but not the outside. No, the doors were never locked. So what's the problem? They only open to the inside. But the problem is, on the outside of these doors, they have these handles, and they don't look like push handles, do they? They look like pull handles. So you pull them by default. Everybody does that. You don't push them, but they would open if you pushed them. The other thing about that is, when you're walking straight through, you don't think about which way is it opening in and which way is opening out. You just think of opening towards you. And so if you pull this one to open towards you, it opens. But if you pull this one to open towards you, it does not open. You have to push that one. Who pulls this one and pushes that one in a straight line? It's just not very intuitive. There's probably a way around that one. Here's another example. So this is a flat horizontal piece of a computer, older computer. This is the vertical piece. All right, which symbol lines up with which hole? This is for a mouse and a keyboard, old school. Green in that case was the mouse, and in this particular version, it lined up with the lower hole, and the red lined up with the upper hole. Does that make any sense to you? No, it doesn't to me. It doesn't to me at all. Here's another one. New style, old style Quaker Oats lid. The old style kind of was flat on top and had a seal on the sides. The new one kind of has an impression on the top, and the seal kind of goes up and over the lip. The problem is, it's kind of hard to grab a Quaker Oats can if you have a small hand. If you're a child, right? Your one hand doesn't really fit around the whole thing. I'm not even sure my hand fits around the whole thing. So if you're going to grab it with one hand, what do kids maybe want to do? Well, that kind of looks like a handle. Oh, and the lid falls off, the thing tips over, and all your Quaker Oats are on the ground. Because there's no easy handle for such a large container, large canister. That kind of looks like a handle to some kids, and now it's on the floor. I like this one. This is a kind of caster rolling file cabinet, file drawer system that you might put under a desk or something like that. It's got a handle because sometimes you need to roll it around. It's also got drawers that need to be opened, and they have these recessed handles, so you grab them. Well, what happens when you forget that this handle doesn't open the drawer? You grab it, and the drawer, oh, maybe it's locked, or maybe it's latched, or something's caught, and I pull it hard, and now you've just jerked your whole filing cabinet across the room, and whatever you had sitting on top of it, because, come on, let's face it, we all know we're going to use that surface for something. Your mouse or your drink or whatever you have sitting up there, your coffee is now everywhere because that handle doesn't actually open anything but the drawer. Oh, and by the way, it's also in the way of getting into the drawer. And then the last one, this happens to me regularly when I go to a restaurant. I want a fork. Where's the fork? I see a lot of handles, and they're all the same. And I don't want to touch the soup spoon handle and the regular spoon handle and the knife handle before I finally find the fork. I don't, but I do. And what do I do when I pull out the spoon and I don't want a spoon? I can throw it away or take it anyway, but usually I just put it back. And now I've just grabbed that spoon and put it back. And so is every other person who's been through this cafeteria line. Disgusting, right? All right, that's it. Make sure that you understand, especially the 4 types of human error: slips, lapses, mistakes, and violations. Those are really important, as well as understanding the vigilance task, the inspection task, and the monitoring task. And there are a few other things in there as well that I emphasized when we went through it.